Welcome to the exercises for DGD 6, which will cover a variety of topics from Cartesian products to functions to equivalence relations and a bit on the division algorithm. So starting with 5.3.2, which is on Cartesian products, we're asked if for any four sets, is it true or false that in part 1, this equality holds, that the Cartesian product of A and B union the Cartesian product of C and D is equal to A union C cross B union D. If this is true, we'd like to provide a proof that these sets are equal, and if it is false, we need to demonstrate so with a counterexample. Now this actually ends up being false. The idea is that here you can only have pairs where the first element is from A and the second is from B, or the first is from C and the second is from D. Whereas on the right-hand side, I could have a pair with the first element from C and the second from B, and such a pair would not occur in the left-hand side. So this is actually false. And we can consider a counterexample. Consider the following counterexample. And to make this easy, I'm just going to use singleton sets. A will be the set that contains little a, B will be the set that contains little b, C will only contain small c, and similarly D will only contain small d. So then we can compute A cross B is the set of pairs where the first element is from A and the second is from B. This means it has to be the pair AB, small a, small b. And C cross D is the pair small c, small d, each only having one element. And this means that their union has two elements, these two pairs. However, A union C contains two elements, small a and small c, and B union D contains two elements as well, small b and small d. And since these each have two elements, the Cartesian product will have four elements. So then A union C cross B union D will contain, well, it'll contain the pairs where the first element is A and the second is either of these, so A, B, and AD. And it will also contain pairs where the first element is C and the second is either of these, CB and CD. So, since this set only has two elements and this set has four, they cannot be equal. So we can just conclude that the first set is not equal to the second set. Part 2 asks if for any four sets this equality holds. We're using intersections. If A cross B intersect C cross D is equal to the Cartesian product of A intersect C with B intersect D. And this ends up being true. So since it is true, we can provide a proof by showing that an element belonging to this set is equivalent to an emblem belonging to this set. Since this is a set made up of Cartesian products, when we consider a generic element, we consider a pair. So let the pair xy be an element of our left-hand set. Since it's in an intersection, this is equivalent to the pair xy being in A cross B and the pair xy being in C cross D. Then, by definition of Cartesian product, this means x is in A and y is in B. This is all still joined by an and to this, which is equivalent to x being in C and y being in D. Now, we can regroup this. Just doing some commuting, we have that x is in A and x is in C. And this is connected to y being in B and y being in D. This is equivalent to saying that x is in the intersection of A and C, and y is in the intersection of B and D. And now this means that the pair will be in the Cartesian product of these two sets. So this is equivalent to saying that the pair xy is in A cross C, sorry, A intersect C cross B intersect D. Now since it is equivalent for this element to be in the left-hand set and the right-hand set, therefore they are equal. Moving on to functions, exercise 5.4.1 gives us a series of sets and asks us if they define a function. And we can recall that a set in a Cartesian product defines a function from the first set to the second set if, for every element in the first, there is a unique pair containing that element in the set defining the function. So we're asking if this is a function, and this is. This defines the function which takes an integer and gives you back the integer which is its square. And so to see that this is a function, for each integer x, there exists a unique pair, a squared, in this set. Such that the first element a is equal to x, and that is the pair. If a has to be equal to x, then a squared is equal to x squared, so it's the pair x squared. And if any other pair was equal to this, well, its first element must also be x, so it must be this one. Part 2 asks us about the same looking function, but now we restrict to the natural numbers. Is this set of pairs a squared, where a must be natural, a function from the natural numbers to the natural numbers? And this is also a function. For each natural number, there is one unique such pair, for the same reason up as above. The fact that x was an integer here wasn't explicitly used. Because it begins with just an element of the set, it will be a function. So yes, for reasons similar to above. Part 3 gives us a set where a squared and a are now flipped. Going back to a being in integers, and we want to ask if this can be considered as a function from the set of squares in the integers to the integers. So is this subset of this Cartesian product defining a function? And now it is not. For elements of this left-hand set here, for elements which are squares in the integers, there can be two possible pairs that begin with that element. So no. Since 1 squared is equal to 1, this means that 1 is an element of this left-hand set in the Cartesian product. So if this was a function, only one pair would be in here, which begins with the number 1. However, both 1, 1 and 1 minus 1, because 1 squared is 1 and minus 1 squared is 1, are in this set. Since there is not a unique element that begins with 1, this is not a function. Lastly, for part 4, we want to look at the same idea. The pairs are a squared and a, where a can be natural now. And we're considering this as a subset of the natural numbers squared cross the natural numbers now. I want to ask if this is a function, and now it is. And this is a function because for any element, which is a natural number squared in our left-hand set of our Cartesian product in our domain, we could have two options, n squared n and n squared negative n fit the pattern of a squared a. However, negative n is not natural, which means that it won't be in our set. So there exists a unique pair, n squared n, in our set. Since each element of the domain has a unique pair in the set defining the function, this is a function. Moving into section 6.1, we'll now be discussing equivalence relations. Exercise 6.1.1 gives us a bunch of different relations defined on the integers and asks us if they are equivalence relations. So to be an equivalence relation, it needs to be reflexive. So x is related to itself for all elements. So this is x is related to x for all integers. It needs to be symmetric. This is the fact that if x is related to y, this implies that y is related to x, and it needs to be transitive. This is if x is related to y and y is related to z, this implies that x is related to z. So we'll either be verifying all these hold or showing which one fails for the following examples. The first, we define x to be related to y if x is strictly less than y. And this is not a relation because it is not reflexive. Sorry, not an equivalence relation. So not an equivalence relation since it is not reflexive. We can show that this fails for any particular integer. So counterexample. 1 is not strictly less than 1. So 1 is not related to itself. Therefore, it is not reflexive. Exercise 2 does away with this issue by instead defining x to be related to y if x is less than or equal to y. So now this is reflexive since the possibility of equality is allowed. However, this now fails symmetry. So not an equivalence relation. It is not symmetric. By a counterexample, we want two elements which are related to one another, but not in the reverse order. So we can say 1 is related to 2, since 1 is less than or equal to 2. However, 2 is not less than or equal to 1, which means that 2 is not related to 1. Because we have a relation 1, 2, but we don't have its symmetric version, this is not a symmetric relation. Part 3 asks about the relation defined by x being related to y if the absolute value of x is equal to the absolute value of y. And this is an equivalence relation. In general, not always, but in general, relations defined in terms of equality end up being equivalence relations because equality itself is an equivalence relation. Nevertheless, we must prove this. We must prove it is reflexive. So to do this, we need any x related to itself. So let x be an integer. Then, since the absolute value of x is equal to the absolute value of x, it satisfies the condition to have x related to itself. So x is related to itself, so it is reflexive. To prove that it is symmetric, we must start by letting x be related to y. This means that the absolute value of x is equal to the absolute value of y. This means that the absolute value of y is equal to the absolute value of x, since equality is symmetric, but this now satisfies the definition to have y being related to x, so it is symmetric. To show it is transitive, we must let x be related to y and y be related to z. This implies that the absolute value of x is equal to the absolute value of y, and the absolute value of y is equal to the absolute value of z. Now, since equality is transitive, this implies that the absolute value of x is equal to the absolute value of z, which satisfies the condition for x to be related to z, so it is transitive. Hence, it is an equivalence relation. Part 4 asks if we define a relation by x is related to y if x is not equal to y, if this will be an equivalence relation. Now, unlike the previous example, inequality is not an equivalence relation. It fails reflexivity. So no, not reflexive. x being equal to x means that x is not related to x. So this is not an equivalence relation. For part 5, the relation is defined in terms of x being related to y if x times y is greater than 0. And the answer is no, this is not an equivalence relation. It's reflexive at all elements except at 0. So not reflexive at 0. And we can see that by the following. If 0 was related to 0, this would mean that 0 times 0 is strictly greater than 0. However, this would mean that 0 is strictly greater than itself, which is a contradiction. So 0 is not related to itself. So this is not an equivalence relation. Finally, we can ask for the one relation which was an equivalence relation, where x is related to y if their absolute values are equal. We can ask what the equivalence classes are. The equivalence class of an element is all other elements which are related to it. And so these equivalence classes are indexed by 0 and the natural numbers, and they are as follows. For all integers, the class of x is equal to the set of integers y, such that x is related to y. This we can rephrase just by using the definition. X is being related to y is the same as the absolute values being equal. So this is the set of all integers with the same absolute value as x, which we know is just x and minus x. And so therefore, this describes all of the equivalence classes. All of them have 2 elements, except for the class of 0, which has 1 element because 0 and minus 0 are the same. 6.1.2 asks us to prove that some relations on the Cartesian product of z cross z are equivalence relations, and after having done so, to determine what the equivalence classes are. I'll prove that the first one is an equivalence relation. The proof that the later examples are equivalence relations are similar because they're all defined in terms of equality, and we'll determine their equivalence classes. So, proof that this is an equivalence relation, we need to show that it is reflexive. To do this, we need to let xy be any element of the Cartesian product, because this is a relation on the Cartesian product. Then we would like to show that xy is related to xy, which, since x squared plus y squared is equal to x squared plus y squared, it satisfies the condition where v is x and w is y. So this means that xy is related to xy, so it is reflexive. To check symmetry, we have to let the pair xy be related to a pair vw, and we would like to show that vw is related to xy. By definition, this means that x squared plus y squared is v squared plus w squared. Since equality is symmetric, this means that v squared plus w squared is x squared plus y squared, which means by the definition of this relation that vw is related to xy, so it is symmetric. To see that it is transitive, we need a chain of equivalences, so let's let xy be related to vw, and vw be related to ab. This means, by definition, that x squared plus y squared is v squared plus w squared, and that v squared plus w squared is equal to a squared plus b squared. Thus, by transitivity of equality, we have that x squared plus y squared is equal to a squared plus b squared, which satisfies the definition for the pair xy to be related to the pair ab. So this is also transitive. Hence, it is an equivalence relation. To see the equivalence classes, we can take an arbitrary element in the set, which is the Cartesian product of z cross z, and we can consider its equivalence class, which by definition is the set of all other pairs vw in the set, such that the pair xy is related to the pair vw. we can rewrite this relation within this set. This set is equal to all the pairs VW, which satisfy this condition of being related, which we know means x squared plus y squared is equal to v squared plus w squared. And so now we're just looking for all pairs such that v squared plus w squared match some number, whatever this number is. So the equivalence classes are then categorized by whatever numbers these can be. So let's let capital K be equal to the set of x squared plus y squared, such that x and y are integers. So then, for all possible numbers in this set, we will get an equivalence class. So to define a set E sub small k, define this to be equal to all of the pairs VW in Z cross Z, such that v squared plus w squared is equal to k. And define this for an element k in big K. And these are all the equivalence classes. All of the elements that add up to some number which is of the form x squared plus y squared. The second relation, which is also an equivalence relation, is that the pair xy is related to the pair vw when y minus x squared is equal to w minus v squared. And so to determine the equivalence classes, we can again let xy be any pair in our set and consider its equivalence class. Well, the class of xy is all of the other pairs vw, such that xy is related to vw. This is the same set as all of the pairs in Z cross Z, such that, expanding this condition, y minus x squared is equal to w minus v squared. And now since xy is fixed, y minus x squared is just some number. So, whatever that number is, we're just looking for all the pairs where this formula, w minus v squared, is equal to y minus x squared. Now since y minus x squared can be any integer, so in particular, note, if a is an integer, then a can be written as a minus 0 squared. So the equivalence class of 0a is equal to the sets of pairs vw such that w minus v squared is equal to a. And since all of these will be integers, there will be one of these. So these are the equivalence classes. So the equivalence classes are the sets EA, which are defined to be all of the pairs VW, such that W minus V squared is equal to A. And this is for any integer A. The third equivalence relation says that the pair XY is related to the pair VW if X times Y is equal to V times W. So by similar arguments as in the previous cases, these equivalence classes are going to be categorized by whatever number X times Y is for the element whose class you're considering. And these numbers X times Y can be any integer, because you can always just take the integer A you've chosen and multiply it by 1. So, by a similar argument, the equivalence classes are sets EA, they're sets of pairs in our set Z cross Z, such that V times W is equal to A, and these are for any integer A. And similarly again for part 4, the equivalence classes of this equivalence relation will depend on the value of x plus 2y for the chosen pair xy, and this can be any value because x can be any integer and we can always pick y to be 0. So again, here the equivalence classes will be indexed by the integers, and they will be sets EA, which are sets of pairs in Z cross Z, such that this expression V plus 2W is equal to the A, which defines the class, and these are for any integer A. 6.2.1 features exercises involving the use of the division algorithm, which we can recall as the following statement. If we have a natural number n and any integer m, then there exists unique integers q and r, the quotient and remainder, such that m can be expressed like this. M is q times n plus the remainder r, and that remainder is between 0 and n minus 1, and such numbers are unique as stated. So we can use this to prove the following statement. We want to verify that an integer m is odd if and only if there exists some q and we can write m as 2q plus 1. Now, this is probably a result you're familiar with. We know the definition of even is that you can write the number as 2 times an integer. However, odd was never defined to satisfy this property. So far, odd was only defined as being not even. So here, using the division algorithm, we're going to show that not even is equivalent to this expression. So proof. What we're going to do is we're going to let m be an integer and assume m is odd. So far, all this means is that this is equivalent to saying m is not even. So these are our assumptions. Now we're going to apply the division algorithm where our chosen n is going to be 2. So therefore, this will produce unique q and r integers such that m is equal to 2q plus r, and r is between 0 and n minus 1, which is 1. So we have two cases here. Either r is 0 or r is 1. So case 1, if r is equal to 0, this means that m is equal to 2q plus 0, which is just equal to 2q. But we know that this would then satisfy the definition of being even. So this implies that m is even. But we know that m is not even by assumption. So this is a contradiction. Hence, case 1 cannot occur. Since case 1 does not occur, there's only one other option. Therefore, case 2 occurs. This means that r is equal to 1, and m is equal to 2q plus 1, which is exactly what we wanted. Because m is odd, we've shown that there must exist a q coming from the division algorithm, and r equal to 1, also coming from the division algorithm, such that m is equal to 2q plus 1. So we have shown that m being odd implies that there exists an integer q such that m is equal to 2q plus 1. We were asked to prove an if and only if statement, so we need to now assume this right-hand side and prove that m is odd. So conversely, assume that there exists a q such that m is equal to 2q plus 1, and we would like to conclude that m is not even. Towards a contradiction, assume m is even. If m is even, this means that there is some integer j such that m is equal to 2 times j. But now we have two different descriptions of m. So this means that 2q plus 1 is equal to 2j. Now we can rearrange this. Let's move this 2q over to the other side. So this means that 1 is equal to 2j minus 2q, where this is 2 times j minus q. However, this means we've written 1 as 2 times an integer. So this implies that 1 is even, which is a contradiction. Since 1 is not even, this cannot be the case. So therefore, m is not even. And by definition, this is the same as saying m is odd. So we've also shown the converse implication, and hence we've proved our if and only if statement. M is odd if it can be written as 2q plus 1. Part 2 asks us to prove this statement, that for any integer n, either n is even or n plus 1 is even. To prove this, we can use our result from part 1. So proof. We need to take an arbitrary n, so let n be an integer. We're trying to prove an or statement. We can do this by cases, as long as we end up with the or statement at the end of each case. And two convenient cases can be either n is even or n is odd. So case 1, assume n is even. Well, if n is even, we already have part of our or statement is true, which means that the or statement is true. So this implies that n is even, or n plus 1 is even, trivially. So in this case, we have our or statement. In case 2, we can assume n is odd. That's the only other case. So now by part 1, we know that there exists a q such that n is equal to 2q plus 1. Using this, we can compute n plus 1. So n plus 1 is equal to 2q plus 1, which is 2q plus 2, which is 2 times q plus 1. This is 2 times an integer. So n plus 1 is even. Since n plus 1 is even, and that means half of our or statement is true, so the whole or statement is true. So this implies that n is even, or n plus 1 is even. Now, in each of our exhaustive cases, we arrived at the same conclusion. N is even, or n plus 1 is even here, and in case 2, n is even, or n plus 1 is even. So overall, we've proved our statement. As a last part for this exercise, we can prove statement 3, which is that an integer m is even if and only if m squared is even. But for our proof, we can just begin by proving the usual direction. So to do this, we assume that m is even. So let m be an integer, or let m and z be even. We know that the definition of even means that there exists an integer j, such that m is equal to 2 times j. Now we're curious about m squared, so we can just multiply this equation by itself. So m squared then is equal to 2 times j squared, which we can write as 2 times 2j squared, since this is just 4j squared, which is what you get if you multiply this out. Importantly though, this is 2 times an integer, so m squared is even. So we get our forward direction. To prove the reverse direction, we instead prove the contrapositive of the reverse. We equivalently show that if m is odd, this implies that m squared is odd. So let m and z be odd. By part 1, we know this means that there exists a q in the integers such that m is equal to 2q plus 1. Now we have a formula for m, so we can just square it. So m squared is equal to 2q plus 1 squared. This is 4q squared plus 4q plus 1 when everything is multiplied out. And these first two pieces can have a 2 factored out. This is 2 times 2q squared plus 2q, all plus 1. But now this piece here is an integer, so we've written m squared as 2 times an integer plus 1, Since part 1 was an if and only if, this implies, again by part 1, that m squared is odd. So since we've now proved that m being odd means m squared is odd, the contrapositive is that if m squared is even, then m is even, which is exactly what we needed to show in our converse direction, so we've proved our statement in general.